Hi, this is Pat Kelly. Okay, in this group of problems, what they're going to do for you is give you the good old force field function, that f function, and we're asked to evaluate this integral, our good old work integral, for each of the paths that they might give us. So like a part A and a part B to the problem. So let's get into it. What I'm looking at here in this first part A, the first path that they give me, is a nice parametric representation of the path. And that tells me that I think I might want to rewrite this integral, something we've seen before, where if I get things in terms of t, the parameter, that integral becomes integral from a to b, the f vector as a function of that t. I've got to dot that with the r prime vector of t, and then of course dt. Okay, so if that's what I'm thinking, let's go to part A of this problem and do that. And to do that, we've done these problems before, where a good first step is to do your derivative, r prime of t, equals, derivative here is just I vector plus 2tj vector. I also like to have my f vector as a function of time. We've done about 118 of these, I think. You're looking at your x and y from here, trying to plug them into there. So I'm looking at 2 times t squared for 2 times x times y. That would be a 2 times t cubed times I. And then a plus from the f, and x squared, I'm going to grab this t and just square it, and that's j. All right, then I'm ready for my integral. Well, let's just go right to that formula. Integral from a to b, I'm going to go 0 to 1. And I can do that dot product as we go. We're looking to dot the f with r prime. So multiplying here, we get 2t cubed plus, and then 2t times t squared, that's another 2t cubed. And we integrate that with respect to time, or t, the parameter. So let's do this because it's going to be convenient for us. 4t cubed, that bumps up to t to the 4th, divide by 4, so the 4's are going to cross out. So you're just looking at t to the 4th from 0 to 1, right? Which is 1. Okay. Now, before I move on, you might ask yourself, Pat, why'd you leave so much space here? I had a reason for this. They gave you a hint in the directions, is if your force field is independent of path, then you get to choose which path you want to take. So you might start these problems actually by checking to see if this f is independent of path. Remember how to check that as you're looking at your partial of m with respect to y, and we ask ourselves if that equals the partial of n with respect to x. Okay, question at first, and we'll get the answer. Not always yes. We'll get the answer, see if it's yes or no for this problem. But we'll do our partials. Partial of m here with respect to y is just going to be 2x. Partial of n with respect to x is also 2x. So do those equal each other? Well, obviously yes. Right. Question, I guess, at first, but the answer is yes. Let me make that a little bit neater. Okay, so what? Well, before I get to the so what, like the punchline, what else we can do once we find that, okay, yes, it is independent of path or conservative, if you remember, is let's find lowercase f of x. So, sorry, lowercase f of xy. And we do that by finding the partial of that lowercase f with respect to x, not by finding that. I think that's what I just said, but not finding it equating it to what we know it will end up equaling, and that's the m up there. So 2 and then xy. And similarly, we know that the partial of that lowercase f with respect to y will equal the n up there, which was our x squared. And we do that because then I can integrate each of these and try to come up with an expression for f, lowercase f. Integrate this with respect to x. X bumps up to the 2 power divided by 2. That 2 is gone, and I'll just get x squared. Y was a constant coefficient. Plus, usually you say like g of y. There might be some y stuff in there. Plus a constant. Let's go to the next one. Integrate this with respect to y. That gives us another expression for f of xy. Integrating this with respect to y, I actually just get x squared y. And there might be some x stuff, and there might be a constant. But, I say might be, there's a but, because then what we do is try to see the similarities and differences, and the similarities are x squared y. So we know that that's in there in my final expression for f of xy. I know the x squared y is in there. I think I left you hanging with a but. The but is I don't know if those g of y or h of x's are in there. They're not, because if there was an h of x, it would have shown up there. If there was a g of y, it would have shown up there. So that's my f of xy. And there is a constant, maybe. I don't even care about that, as you'll see. Now let's do the second part of this problem, where this is a different path that the object might take. And I'm going to capitalize on the fact that this particular force field is independent of path. What that means is I actually don't even care, what's going on in between the beginning and the end. All I care about is the beginning and the end. So let's find those beginning and end points. To do that, you're just plugging in your first value of the parameter and your second value of the parameter. So at first, put in the 0, here 0, here 0. That tells me that x comma y is 0. Now let's find out where it ends by putting a 1 in. Here's a 1, here's a 1. It goes from 0, 0 to 1, 1, which means I can get that integral, the original integral that they asked me for. I'm just rewriting right now. The original integral that they asked me for, I can just go right into my antiderivative, that lowercase f that we found, x squared y. The reason why I said earlier I don't even care about the constant is because this is going to be a definite integral from 0, 0 to 1, 1 in this case. So the constant subtracts out. We've seen that before. So let's just evaluate this. Plug in 1 and 1 for x and for y, and you get 1. Put in 0, you get 0, and you get an answer of 1. Okay. I would definitely argue the integration was very smooth here. Okay, quick answer. But you did have to do some preliminary work up here to see that the force field's independent of path. However, it's going to be shorter in the long run. If it's independent of path, this is going to be a much quicker calculation for you. All right, let me wrap up this problem by making another comment here, comparing what I did. If I were you doing these problems, start with your check for independent of path. Because if the answer is yes, then you can jump right into this short work for as many paths as they give you. So yes, I could have done that for this first path that they gave me. The reason I didn't is because in another problem that you might work on, the answer might be no, it's not independent of path. So you would do this approach for all the paths that they give you, okay? Another reason I did it this way is because you're not wrong to do it this way. You will get the right answer, okay? All right, practice some more on your own. You'll get confident with it.